So let's do 13 for starters, 113. I'll put the, if you tell me, I'll put the page number so you'll know there's no, anybody want to read that? I can read. Here, tell you what. Here's my book. If you want to know what I'm going to cover today, it's basically going to be through we're going to finish the stuff you need to know in this chapter, if I have my way. And then we'll get into chapter 2. Most of this stuff you're going to see is just small changes in what we've already talked about. We're going to talk about permutations. We're going to talk about basically what he calls counting. But go ahead. You got it?
Is it the mutual fund company?
Yeah. Go ahead.
A mutual fund company offers its customers several different funds.
Isn't this part of the homework class? All right, go ahead.
A money market fund,
All right, I'm just going to call it money market.
3 different bond funds,
All right.
short, intermediate, and long term. 2 stock funds, moderate and high risk,
All right.
and a balanced fund.
And then a balance. All right, go ahead.
Among customers who own shares in just one fund, the percentages of customers in the different funds are as follows. Money market, 20%.
All right, 0.2, go ahead.
Short bond, 15%. Intermediate bond, 10%. Long bond, 5%. High risk stock, 18%.
Oh, sorry.
What is SM for?
It's medium risk stock, or whatever you call it.
Moderate risk stock
Moderate.
is 25%.
What else?
Balanced is 7%.
All right, now I hope these all add up to 100. That's how it's distributed, right? All right, so we would call this the distribution function, and we'll get to there. You're going to see this in chapter 2. But this better add up to 1. So just out of curiosity, let's see. This and this is going to be 0.2, 0.3, and then 0.55. Yeah, it's 1, I think. You can check me on that. Okay, now what's his first question?
Well, first he says a customer who owns shares in just one fund is randomly selected. And then part A is, what is the probability that the selected individual owns shares in the balanced fund?
All right, now what he's telling, he didn't say it explicitly. There's an equal likelihood of the person owning stocks in any, I should say not equally likely, but the person can own stocks in any of these things, and this is the probability that they own it. Now, what did you say now?
What is the probability that the selected individual owns shares in the balanced fund?
All right, so the balanced
7%.
fund, where is that? This is balanced, right?
Yes.
It's just 0.07 or 7%. Y'all 0.07 or 7%. Y'all with me on that? That's it. You're just looking and seeing, oh, that's 0.7, that's it. What's the next part?
What is the probability that the individual owns shares in a bond fund?
All right, now first, let me put this down. A, so if you just want to talk about the balanced fund, it's 7%. Now B is the
It's-
bond fund?
Yeah, the short intermediate fund.
All right, just add those up. That's all it is. So this is going to be, that's 0.2, 0.3. So this should be in the bond fund. It should be 0.3 or 3, no, sorry. 30%, sorry, 30%. Now, is that, do you have the answers, anybody? Is that right? I mean, they're in the back of the book. Is that right? Okay, what's next? This is just looking and adding simple numbers.
What is the probability that the selected individual does not own shares in a stock fund?
All right. This is just 1 minus the probability they do. Do you all follow me? In a stock fund. So part C, this probability is going to be equal to 1 minus the probability that they do own stock, right? You said stock fund.
Yes,
isn't
sir.
it? All right, what are the stock funds?
High risk stock is 18% and moderate risk stock is
So it's 1 minus these two. I think he has a wrong answer in the book, or he shows a wrong mathematical operator. So it's 0.25 plus 0.18. Is that right, class? What is that? That's going to be 0.75. 0.57, that's right.
that's correct.
57 or 57%. Go ahead.
That's correct, and that's the end of the problem.
All right, y'all follow me on this? This is just getting you acquainted with the terminology and the way to do business. There's nothing here that's really taxing you. All right, and there's no Venn diagram. We could draw one, but it's not necessary for this. It's just inspection. What's the next part?
That's it for number 13.
All right, and how about 15? I think my next one is 15. I'm doing these things because this is where you'll become aware of a lot of things, in my opinion. I go through these things, and people are getting it, and then there's a point, they don't get any of it, what I'm saying. It just happens, and this particular course is the worst, in my opinion. The other courses, it's deterministic, but probabilistic stuff's crazy. How about we do 115? What page is that on, by the way?
15 in the book.
Page 15 in the book. Okay, go ahead.
A computer consulting firm presently has bids out on 3 projects. Let A sub I equal awarded project I.
Award.
Okay.
Go ahead.
For I equals 1, 2, 3.
I equals 1, 2, 3. Go ahead.
And suppose that,
A3, right?
yes, correct,
Go ahead.
equals 0.07.
And then we have to have P, all of them, yeah. A1 intersect A2 intersect A3 equal
0.01.
All right, 1%. Now, this is where Venn diagrams come in useful, and I'll try to show you this. Stop me at any time if you don't understand. How many tried this again? Okay, if you haven't, be real attentive here. Here's where people get destroyed, in my opinion. So the Venn diagram gives you like a visual representation, an aerial map of what you think of in terms of probability. Probability is really a ratio of areas in a way. You can shape it like that. So here we go. Here's a set of all possible things that can happen. Now, I know that there's overlap, so I'm going to call this A1, and these are just areas. This is A2, and this is A3. I'm just drawing this so you can see it, all right? Now, if you think about this from an area perspective, if you wanted to know, and hear me, and just look at the areas. If I wanted the area intersecting between A1, A2, and A3, hear me now. If I wanted to know that, by looking, without putting numbers on, you all see it's this right here. That's the intersectional area, right? If we take the area of A1 plus A2 plus A3, and we wanted to know just the total area, these, not the individual areas, but if you think about the footprint that they have on that set, what we'd have to do is take A1 plus A2 plus A3, then we'd have to subtract out this area, subtract out this area, and subtract out this area, because we would have already added that. Do y'all follow me, class? Then we'd have to what? Add this area because we subtracted it off. Now I want you to just think about this rationally. Do y'all see that? Because we've already subtracted it when we did these areas of overlap between just 2 of them. We've already, so if you looked at this, you probably understand. I'm going to write it over here so you see it. This is actually a pretty good problem to give you an idea of the things you need to think about. And probability is really, you can think about the areas, the probability is proportional to the area. So when we take a look at, what does he want now?
Express in words each of the following events and compute the probability of each event. A1 union A2.
A1 union A2, is that right? Okay, now the probability of this is what I'm gonna get at. So it's gonna be A1 union A2. Now take a look at this for a second. If they were disjoint, if A1 and A2 had no overlap, it would just be the probability of A1 plus the probability of A2. Y'all follow me in that? It's proportional to the area. No overlap, just add the areas. But there's overlap. So what we do is say this is probability of A1 plus the probability of A2. So I'm adding the two areas, but then I have to subtract out this area of overlap that I've counted twice, or have counted, right? So then I subtract off P of A1 intersect A2. I'll write this down. Is everybody with me on this one? How many see this? Just to make sure. It gets weird though, trust me. So if you take a look at this, I got A1 is 0.22, help me out here. 0.22, A2 is 0.25. And the intersection of A2 and A1 is 0.11, right?
Yes.
So 0.11, what is that gonna be? Zero, is that right?
Yes, sir.
All right. Or 36% like that, if you wanna do it this way. That's A. B, go ahead. I had him before, that's the reason I'm calling.
A1 not intersects A2 not.
A1 not, go ahead.
Intersects A2 not.
All right, this is a good one. Now, I want you to think about this. We're looking at everything that is not A1 and A2. You all follow me, class? Everything that is not A1 or A2. So if you think about that in this map, now just look. Here's A1, here's A2. What's everything that's not that? Well, all right. Everything that is not A1 or A2 is what they're asking for. That's why, well, it's all this area in green that I'm showing you out here. Can you all follow me on that? Give me everybody with me. So what is that gonna be? Well, how could you get it? Probably several ways. If you take a look at this, what would you do? I know what? I know the area A1, A2, right? We just got that, right? So 1 minus that area, if you think about it, would be the outside area. Do you all follow me? We've got it, so this is right here is equal to 1 minus, if it's probabilistic, we could do area-wise, probability of A1 intersect, or union A2. So that's gonna be 1 minus, and what is that, 0.36, is that right?
Yes, sir.
0.36, so that's equal to 0.64, is that right?
Yes, sir.
All right, is that the right answer?
Yes, sir.
Now, the way I think about this though, this is not A1, this is not A2, it's an intersection. So it's everything that is not either of these. Now, there's, I think, De Morgan's theorem, you can break that up into other things, but just looking at that in terms of interpreting what the statement means and looking at the map, can everybody see this? What if I said this? I'm gonna just, give me a second, we'll continue on. What if I said I want the probability of everything that's not A1 intersect with A2 intersect with A3? Not. Everything's not, all right? What are you gonna do? You're gonna what? Just blacken these circles and look at the area outside that, right? Or take 1 minus the probability of all these. You all with me? Can you all see that, class? We're gonna get to that in a second, but I wanna make sure visually you got a good idea of this. I'm not being exact with my language in terms of areas, proportional probability, but that's what a Venn diagram's supposed to do. Give you a mental image of what's happening with the probabilistic world, where the actual probability of events have to do with the area on the Venn diagram map. That's the idea. And it's a useful tool to start with. So what's the next one?
A1 union A2 union A3.
All right, probably A1. This is a good one because you can do the logical extension. Now think about this for a second. in terms of the areas being proportional to the probabilities. So if I wanted that, what I'm really looking at is what? I'm looking at all that area, all this area, right? And I have to subtract off the overlaying areas, right? And then I have to add that middle one. Do you all see that? I think he does it the same way I'm doing. So for this one, it's going to be what? Well, it's just starting with probability of A1 plus probability of A2 plus probability of A3. That's the starting point. And if they were disjoint, if there was no overlap, that would be it. Everybody with me? Then you have to got to get rid of all the overlaps. So it's going to be minus the probability of A1 intersect A2 minus the probability of A1 intersect A3 minus the probability of A2 intersect A3. But I've subtracted off that half, this sliver, and this sliver, but I've subtracted off that area in there, so I have to add it. You all with me? I basically subtracted it twice. So then I have to add plus the probability of A1 intersect A2 intersect A3. Now, does he have that in the answers, something like that? All right, now put the numbers in. I want to make sure they agree because I'm always a little suspicious about some of these things. So for here, A 0.22 plus 0.25 plus 0.28, right? Then it's minus, I'm just going to put this 0.11 plus 0.05 plus 0.07 and then plus 0.101, pardon me. Now, what does that equal to?
5.3.
Is that right?
Yes.
All right. Again, you have to use this as a visual tool to do this kind of stuff. And it can get a little irritating. That's only with 3. If you have 6 or 7 or 8, we're going to show you how to do this in a general form. All right. But every time you add another one, if you had an A4, first you have to add up all of them. With me? All the probability. Then you have to subtract off all these half moons. Then you have to add in the pieces you missed there. Then you have to subtract off some more. But we'll get to that. We'll get a formula, the generalized formula. And I don't try to irritate you with this, but at least you have to appreciate what's going on. With me, class? Is there another part to that problem?
A1 naught intersects A2 naught intersects A3.
Okay.
Just the opposite.
Yeah, that's kind of nice in a way, right? I'm going to leave that one there, just erase this one and this one. I don't want to bore you with this stuff, but I found this particular part of the course, if you understand it, it really helps the rest, I believe. All right, so this one is D?
Yes, sir.
Go ahead. Probability of?
A1 naught intersects A2 naught intersects A3 naught.
All right, not. All right, now for this one, I think you have an idea what's going to happen. It's this thing, right? We've got the probability of A1 union A2 union A3. It's that area, right? So 1 minus that would be the probability of it not occurring, correct, class? Here, when it has A1 intersect A2, it's everything that isn't them. That's the idea. Everything that is not A1, A2, and A3, correct, class? So what's that going to be? Should be 1 minus 0.53, right? Or 1 minus this. Do you all agree? And is it that? I don't know.
Yes, sir.
What is that? 0.47? Okay. E. Is there an E?
Yes, sir.
I think this is the weird one.
It's
No, this is one, it's got a, yeah, go ahead.
A1 naught intersects A2 naught intersects
Oh, wait.
A3. Just A3.
Intersects A3, good. All right, so now we need a visual on this. I'm gonna try to draw it. Okay, so this is S. once you understand the area involved, I think you get it. First part is A1, anything that is not A1 or not A2. With me? All right, now look. Here's, sorry. Everything that is not that is the first part, right? Y'all follow me? Just take a look at that. If it's not A1 or A2, it's everything but that, including this right here, right? Y'all with me? Now, and is, it says, right? And is what? This right here. If it said not that, then we go outside that one, but it says, and is this. So, oh, pardon me. I got that drawn wrong. I didn't mean to mess it. Let me just erase this thing. You'll see. I think, does he give you those Venn diagram pictures in the back?
No, sir.
All right. Here. All right. Not A1 or A2, outside of that and outside of this, right? But it has to be part of A3, right? All right, so can you all see that what I drew over, I mean, everything outside of there and there is what's my hands not covering, right? But it has to be part of A3. So you see how it's this right there? Can you all see that? Not A1, not A2. Cover them up. Can't be that, but it has to be part of A3. So it's this area. Can you all see that? What is that area? Well, start with A3. Do you agree with that? So we're going to say, for this one, it's going to be the probability of A3, and then what? Take a look. I want this area here.
Subtract all the intersections.
Subtract this intersection and this intersection, and then add this part, because you subtracted it twice. You all with me on this? So let's see if this works. So it's that area, and then it's going to be subtract P of A1, A3, right? Minus P of A2, A3. And then it's going to be this, we have to add it, plus the probability of A1 intersect A2 intersect A3. Let's see if this works. So this one, probability of A1 intersect A2, intersect A3 is really going to be, let's see, probability of A1 is 0.22, right? 0.22 minus, what is this? Just read it.
I think you meant point, for A3 it's 0.28.
Oh, I'm sorry, 0.28, my bad. Can you read it to me?
A1, A3 is 0.05.
0.05 minus,
0.7 or 0.07
and this?
plus 0.01.
Can you tell me if that's the right answer?
It's supposed to be 0.17.
Yeah.
Is that right?
Yeah, that's right.
All right, 0.17. But you all see what happened, how we did it. That's why these Venn diagrams are useful. If you can see it, visualize it with a Venn diagram, you can get the probabilities usually. Because the areas are proportional to the likelihood or probability of the event occurring. You with me? All right, you want to do one more?
Oh, this one has parentheses. So it's start parentheses, A1 naught intersects A2.
Oh, let me, I'll draw it. I'm gonna erase this and do it. These irritate me sometimes. Go ahead now. This is part F, right?
So inside the parentheses, well, it's probability of.
Oh, no. Okay, so they got the first operators A1 naught, A2 naught intersect, right? So we want probability of, and then he has A1 naught intersects A2 naught. That's everything is not these. Go ahead.
And then
Intersect.
union A3.
All right. So first, let's get this, all right? Intersect A1, A2, everything that's not A1 or A2, you with me? And I'll draw it over here. I hope you can see this and I hope you appreciate it. Take a look at this. Here's A1, A2, A3. All right. Now, he says everything that is, start with this, not A1 or A2. Let's see what we're looking at. With me? So what I'm going to do is this, just draw a perimeter like this. And everything outside that perimeter is not A1 or A2. With me, class? Now, it says, and so it's all that area or A3. With me? It says, this means it can be that or it can be A3, right? Now, just follow me on this, guys. So what's left? It's all this area which we can get. Do you agree with that? And then it's what?
All of A3?
It's this additional area right here. Because, I mean, it's basically, it's all that area plus this area. Can you all follow me? With me? So do y'all follow me on this, guys? Get a visual on this. Please just take a look at this one. This one's tricky. The not part says anything but these two. So you can almost erase that. But then it says, and it unions, so it means and A3. Now, A3 is included right here, but A3 is also here, here, and here. So we have to add this, right? Add this and then subtract that. Do you all agree with that, class? Let's try that. So for F, the probability of A1 complement, A2 complement, union A3 will be equal to, first, I'm going to get everything that's not A1 or A2, all right? So that's what? 1 minus the probability of A1 union A2. I think we did that in a prior one, didn't we? Was that the first one we did, class?
Yes, sir.
All right, so we got that. We'll put that down. Now I've got everything in that purplish color. Now I have to add that. So I have to add plus the probability of A1 intersect A3. So I'm adding this half moon slice, then I'm going to add the other half moon slice, so it's going to be, or I should say sliver, it's not a half moon, plus the probability of, and this is going to be A3, A2. All right, so I got this one, and then I have to subtract that middle one because I've already added that in. Y'all follow me, class? So it's going to be subtract minus the probability of A1 intersect A2 intersect A3. Let's see what that's going to be equal to. I'm trying to do this in a rational way so everybody can appreciate it. Okay, so what happens? This probability right here all right, so I got one. What's the first answer we got?
36%.
All right, plus, what's this? What is it?
Oh,
0.28? Is that right?
0.05. Oh, wait, no, it's
0.05.
yeah, it's 0.05.
What is?
A1, A3.
Intersection? I mean, the intersection of that?
It's
Yeah,
written right there.
it's-
It's 0.05.
It was
0.05, yeah. So it's gonna be, hold it. I got this right, that's right. Then it's gonna be plus 0.05, right?
Yes, sir.
Plus
0.07.
0.07, and then minus 0.01, right?
Yep.
And what is that equal to, tell me?
0.75.
Is that right? Is it
That
0.75?
That is correct.
All right. I hope, try to just see this in these vents, that's the reason for it. If you can visualize the area and you realize the area is proportional to probability, you can get the probability. You with me, class? All right. Is there another one too?
No, that was it.
Oh, thank God. Tired of putting circles. All right, so that was 15, right?
Yes, sir.
So would you say working these with the Venn diagrams is more like reasonable and easier than trying to do it like with the axioms, like the?
If you get the axioms, no, I'm just level with you. I can see that. Those axioms, I don't have a visual, like, tool to use, and that's the reason I put that down. You can write, I mean, De Morgan's theorem, all that stuff works, but when you play around with these, and I'm gonna say one other thing. Now, I give you a set of problems. That's sort of the base, that's the minimal you wanna do before class. I recommend, if you want it, people ask me, so what do I do to get a great, a high grade in this class, like an A or a B? Just don't do that. Do as many problems as you can in between. If you want the answers, I'll give them to you. See me after class for all of them. For any of the. But I'm going to tell you this much. The more problems you work, try it on your own, and then check and see if you get them. It'll help you more than anything. I think I said this, not to this class, but I know I said this a lot to my classes. When I was sitting where you were, the one thing I learned that is more beneficial than just re-listening to the lecture or anything like that, or looking at your notes, is doing problems. When I had EMAG and stuff like this, we had hate, and they had the answers to every odd problem, and they had a ton of them, 60, 70 problems at the end of every chapter. I would do every single problem that had an answer if I possibly could, and I usually did. And I would find, if I had it wrong, if I didn't get the answer, didn't understand it, I'd go and ask the professor or somebody. And that, I think, was one of the single reasons for how well that I did it in general. Not, I had other problems, but I'm telling you, that's a secret. If you haven't found that, then appreciate what I'm telling you. If you really want to learn this stuff, do as many problems as you can, because it will make the concepts real. You'll understand how to apply. Okay, now, enough of that. 31? Okay, we'll do 31.
Like an ATM question?
This guy picks out some doozies. He's got stuff in there about craft beer or anything. What would students be interested in? Craft beer. Sounds like something in my life. He's going to talk about combinational information, how to take combinations, and he's going to talk about, give me 1 second here. All right, I'll get to that in a second. Let's do 131.
It's on page 25.
Page 25?
Page 31 of the PDF.
Page 25 of text. Page 31 of PDF. Okay. Go ahead.
An ATM pin consists of a 4-digit sequence. Okay. How many different possible pins are there if there are no restrictions on the possible choice of digits?
This is a no-brainer, but I want to say something. So he does not qualify. So you could put A, B, C, D, E, F, G. If you all follow me, he doesn't qualify. He's talking about digits from 0 to 10. I mean, basically from 0 to 9. You all with me? So if you think about it, it goes everything from 0, 0, 0 to 9, 9, 9, 9. You all follow me? This is a counting sequence. So if you look at how many different digits there are what? Add 0 to 99, add 1 to 99, 10, what? 10,000. That should be the right answer. I don't know if he's got that or not. That's just simple. Now, if it had A, B, C, D, E, F, and all the other stuff, then what happens? Now, instead of counting base 10, you're counting base, what, 26 plus 10, 36, right? Now that number is astronomically large. But you all follow me on this, class? And that's one thing about this book. Some of the things he doesn't qualify. And I guess on my pin number for my Tiger Teller, it's only numeric. But in a lot of things, it's alpha. You can use the alphabet and you can use numeric, like my passwords and stuff like this. They tell you have to use a special character, a capital letter. You have all these other things, and it has to be a certain length. And the reason is because it causes an astronomically large number of possibilities. So when people try to crack your code, it literally takes too long. It's like, do you know what Bitcoin is? You know, they mine Bitcoin. Bitcoin is a solution to a complicated mathematical problem that, from what I understand, replicates how banking is done. I'll say this because we're about to get into some stuff that deals with this. How many have heard of Bitcoin? It's a, quote, cryptocurrency, right? No government is really underwriting it. So if some government decides to take out all the sites where the information is stored and the blockchain fails, then you're left holding the bag. You can't cash out, it's gone. However, it's pretty clever the way they did this. Real banking does one thing. When it has electronic currency, anytime electronic currency is transferred from one bank to another, any amount, all the other banks that do that are made aware of that transaction, and they're pointed that particular money that's valued, and it's really a digital type of thing, is now goes from like the Bank of London to the Chase Manhattan or something like that, and they know, everybody knows where that is. So if anybody tries to spend that electronically anywhere in the world that uses these banks, and it isn't coming from that bank in their account, it'll flag it. You can't. It prevents the double spend. But the way they create these streams of numbers to do this is with very large prime numbers that solve a mathematical problem that we'll get into later in this course. Does anybody own Bitcoin here? I'm very curious.
And
Ethereum, all right. Cryptocurrency. Anybody own crypto? So a lot of people do. Dr. Reeves, who used to teach this course, owns a lot of Bitcoin stuff, and he's a very clever man at the way he organized it. So whenever the likelihood and the probability it goes down, he sells and stuff, he takes it out of there. But it's a very interesting type of thing. Also, it drives the governments nuts because they can't really track it and tax you. I don't know if it's going to survive. So I'm not telling you to buy Bitcoin. All right. Now, I also do 119, 120 before I get into permutations. All right, so now I need my book for a second. All right, so now we're talking about a section in counting. Didn't I ask you to look at the section in counting?
There is more to report.
Okay.
Problem 31.
Go ahead. I'm sorry, go ahead. My bad.
According to the representatives of the bank, there's certain things that are prohibited, like you can't have all 4 digits identical.
All right, so it gets rid of what? 0, 0, 0, 0, 1, 1, 1, 1, 2, 2, 2, 2, and 3, 4, 5, 6, 7, 8, and 9. Or there's a total of 10 there. Go ahead.
And then you can't have ascending or descending sequences such as 6, 5, 1, 3.
All right, this is the counting thing we're about to get into. So you can't have 1, 2, 3, 4. We can't have ascending or descending.
Right.
All right, this is where counting comes in. Did you all look at this problem? All right, so now we talk about permutations. What's that?
I was just letting him use
Oh.
my electronic copy of the book.
Oh, here, I'll give you.
Well, he's got it now.
Oh, okay, you okay?
Yeah.
Okay. All right, so now.
I took off all the bad stuff before I handed it over.
All the bad stuff. Yeah. Pay your dentist. So I'm trying to find out where I'm looking at this.
Can you navigate it?
All right, so now we look at something, this is on page 20, called permutations, and then we take a look at something on page 22 called combinations. And I'm going to try to make this, I'll just read the definitions. And what I want to do is, I'm going to erase that. I'll get to this problem, finish it up in a second, but I need to do these permutation things. What did I do with it? Oh, covered it up. While I'm doing this, is it gonna rain today?
I
More?
don't think so. It's supposed to be cloudy on Thursday.
I could use a day without rain. All right, so I'm just gonna tell you what the definition, it says, definition for, these are permutations and what they mean. So what is a permutation? Suppose I'm gonna have the possibility of a 1, a 2, or a 3. So how many different ways can you take 1, 2, and 3? I think I said this wrong last time, I made an error. Now I want you to just follow me on this. You can definitely go 1, 2, 3, right? That's one way of taking singles. Then you can do what? You can go 1, 3, 2. I'm just reversing the first two, correct, class? Then you can reverse these two. You can go 2, 1, 3, and then you can go what? 2, 3, 1. Do y'all follow me? Finally, you can take the 3 and put it in front. You can have 3, 1, 2, and 3, 2, 1, right? So how many different combinations are there? 6, right? By inspection. Y'all follow me? There's no other ones you can think of, right? I think last time I didn't show you these. That was my bad. Are you with me, class? These are permutations. Now, if there were, and I'll get to this, if you wanted a formula, he does it in the book. He shows you this at the top of page 21. He tries to give you a development of it on how, if you have n numbers and you want to take k at a time, how many different combinations are there? He shows you this. He doesn't go through a rigorous mathematical proof, but he says, well, if you start with one, and he's going to say if you have n values, n would be the first one. Then what you're left with is n minus 1 times that, then n minus 2, and so forth. Down you get down to the kth value. But I'm going to just spare you that. Read it on your own and try to do it with small numbers. Like start with 3, like I just showed you here. Does everybody understand this? That should make perfect sense. So in general, and he uses this symbol, which I'm not a fan of, but he uses, for permutations, it's n, and then p for permutations, k. What it means is this. If you have n, or you have an ordered sequence of k. So what it means is, now suppose all the values in n have numbers like 1, 2, 3, 4, 5, 6, 7, or A, B, C, D, something unique about them. How many different ways can you take k items out of that? You all follow me on this? How many different ways? Like here, if we had 3 elements, how many different ways can you, for 3 ordered elements, 3 distinctly different, can you order them in like this? Where they would have unique values, like this is unique from this and this and this and this. There's 3 values, right? And I want to see how many different ways I can order them. If I had 4 values, I'd have to take this sequence and I have to expand it, and you can see it's going to keep going. So the formula for this is just going to be n factorial over n minus k factorial. That'll give you the value. Promise you. Now, it says if you have n things and you want to get ordered pairs that are k long, this, and they're all unique, this is how you do it. By the same token, if you have, now the next thing is combinations. I'll put it over here. This isn't going to make a lot of sense to you until you do it. When you have combinations, you're going to have n items, but we want to know how many different ways we can take k of them, and I'm trying to say this in a way it's going to be meaningful. For that one, if you talk about this is 3 items. We could have many, many more. We could have, all the way out to 10. Just count the 10 out there. How many different ways can you get, or how many different values can you pull out? Well, 1, 2, 3 would be considered a single value. 1, 2, 3 is here, it's here, it's here, it's everywhere, all right? Y'all follow me, class? So if you talk about combinational items and how many ways you can take them, if you have n possible values out there, and you wanna know how many combinations can be made of K length. Now, that means, for instance, this, the difference between this and that is, if I talk about this with cards, all right? Suppose I wanna know how many different ways I can get a king, a queen, and a jack face cards. You all follow me? How many different ways? Well, first of all, how many face cards are there in there? It's 4 times 3, 12 face cards, correct, class? And how many different cards are there? Forget the jokers.
52.
52. We could write this formula and do this. We're gonna apply this to different things. But if we wanted to uniquely find out how many different, say, king of spades and then other ones, queen, king of hearts, an ordered pair like this, then we would use this, and I've got to show you the difference. Anyway, for this one, it comes out to, it's n factorial over n minus k factorial, but then it has k factorial down here. It's going to divide by k factorial. And I'm going to try to do something that makes sense with this. You know what? I think what we can do now is go to 31 and do that problem. After I put this up, we finish it. So for problem 31, this is 1-31. It has a thing about 4 digits, right? We found that there's 10,000 different combinations, right? Or different possible 4-digit sequences, right? Now he asks something else. What was the last one? You don't have the book. Here. Now for 31, I'm going to try to finish this again, because you'll see this at work, I hope.
There is restrictions on the choice of digits. The following choices are prohibited. All 4 digits identical.
All right, that's going to be 10 possibles, right? There's 10 right there. Go ahead.
Sequences of consecutive ascending or descending digits.
All right, now, here's where this comes in. All right, we have $10,000 possible combinations, right? Let's see if this works. So we have 10,000 possible combinations. And I'm going to tell you this. I'm going to say this right. For each one of these, we have the numbers 0 to 9. So I'm going to say this. If you think about this, there's a probability of 1/10 of each one of these being, any number randomly being selected there. And when they talk about the combinations, I'm not going to say this right. I'm trying to say it in a way that makes sense. This becomes, I gotta think about this, 10,000 possible. And because it's the sequences, it's out of place, I'm not gonna be able to say this correctly. I'm not gonna get this. Can't do this unless I do something else to show you this stuff. Let me see that book for 1 second. Sorry, I'm stumbling on this one, but I'm trying to do this without doing conditional probability. So for 31, it says right here, we have a total of, for this one, if you looked at this, if we have just 3 numbers that are unique, how many different ways can we take it? So it would be 3, and this is going to be 3 at a time. So it would be 3 factorial over, that doesn't make sense. That's 0. I mean, that's going to be,
0 factorial is 1.
that's, yeah, but it's, minus 3 factorial is 1, so that's 1 times 2 times 3 or 6. It does work there. If you got 3 numbers, how many different ways that are unique? How many different ways can you take them? It's going to be n factorial over 3 minus 3 factorial. Then, this is not going to,
What are the restrictions?
if you look at the permutations over here, if you think about this, remember, this is just, all these have the same numbers in them, 1, 2, and 3, because it's without replacement. So if you look at this, for combinations, if you have 3, then you get 3 factorial over, and this is 0 factorial, and then it's gonna be 3 factorial, and that's 1. And you see that for this one, we only have 1, I mean, basically, all these things are the same numbers, just reordered. All right, so that's sort of the difference with combinations, but I'm not saying this the way I'd really like to state this thing. Anyway,
You're saying the combination doesn't care about the order as long as it's the
That's
same
right.
3 numbers?
that's actually, it's better said than I did, yeah. It doesn't care about the order, just that they're there, that's the only thing. Now, when you talk about the ordering of sequences, 1, 2, 3, or 1, 2, 3, 4, 4, 5, all this stuff, what you have to do is do a deep think on this one and think, how often do they occur? If you think about these numbers right here, if you think about ordering, this is ordered, this is not ordered in terms of 1, 2, 3, right? This is 1, 3, it skips 2 and goes to 2. If you think about this one, this is not ordered. This one is not ordered because they're either have to all be going up or down, so this doesn't work. This doesn't work, but this works right here. So if you look at this, it's 2 out of 6 are ordered. Now, if we extended that to 4 digits, right? Then what happens? Well, instead of having 6 combinations for 4 digits, you would get, this one would be what? If you have 6, that's gonna be 6 factorial over 0 factorial, and that's 1 times 2 times 3 times 4 times 5 times 6, and that's gonna be what? It's 6, 24,
Is it 520?
I'm not even sure, 520, something like that?
720.
All right, 2 times 3 is 6, 6 times 4 is gonna be 24, times 5, 60 times 6, 360, is that right? Sorry? 720 for the total? If it's 720, that's the number of these, and how many of those are gonna be sequenced? This is the one thing I'm trying to think of a quick way to do this. Because it can go backwards too. Pardon me?
Can you just multiply by 2 for forwards and backwards?
Oh, yeah, you can, but the problem is there's 6 sequences here, but if it's, or, I mean, this is 2 out of 6, but when you get to larger, it's gonna change radically. I'm trying to think of a quick way to do it.
Oh,
This
okay. I
escapes-
think I have to find a way. Just can I write down or show them? So if we think about the first combination is 0, 1, 2, 3, since that's definitely ascending and it's like consecutive. And if we just write out the last digit, it's just be 4, 5, 6. Taken up to 9, so there are like, and that will be 7, 6, so there will be 3, 1, 2, 3, 4. Like there will be,
7.
yes, definitely there will be 7 for ascending sequence, and for descending sequence,
6.
there will be like,
6.
oh, okay.
No, wait, actually, yeah, you're on the right track. You're building
Yeah,
that
yeah,
right.
it's 7.
That's right, 7.
And in descending, it will also be 7 because of symmetry, so it will be total 14.
And if that may, you probably are right about that. I'm trying to think of a way with formulas to get that.
Yeah.
Right.
Yes, sir. I love with you. I'm gonna have to take it careful. I'm trying to find the combinational way to do that. You can do this with those combinations, but it escapes me the easy way to do it. You have to say if you choose one, the other one, let's say your first digit's n. The next digit has to be n plus 1. After that has to be n plus 2. After that, n plus 3.
Yeah.
Y'all follow me? Then you have to, if you can get that, what's the probability of this, right? And then n can have the values from 0 to 6, I think. Because, right, if you start with 0, then 1, 2, 3, 1, then it'd be 2, 3, 4, 2, and so forth. So it's n, n minus 1, n minus 2, n minus 1, n minus 2, n minus 3, and then you'd have to sum from n equals 1 to, let's see, 6, and that would be the sequential stuff. Let me get to that next time, okay? I'm sorry, I should have gone through this in more detail last night, but I actually, this is, for the combinations, it's fairly easy. But I wanted to do one other thing. I'll get to this on Monday, and I apologize for not getting this down right. Anyway, when we talk about permutations and combinations, this one, that one actually is pretty good right there. The next thing I have to talk about, this is on page 43. I've got to do this with conditional probability. All right, now conditional probability is this. Suppose you want the probability that A occurs given B occurred. Let me give you an example of this before I write the formula down. Suppose you think about a coin toss, all right? Every time you toss a coin, it doesn't depend on the prior events. You all follow me now? If it's a fair coin, if you toss once, you get a heads or tails, 50% chance. Second one doesn't depend on it, right? But if you talk about, suppose you have printers that are made by two different companies. Doesn't matter what the companies are. And they make both laser and they make, say, inkjet printers. So if you given the fact that company A's printer was selected, what's the probability that's a laser or an inkjet? You understand it would just be 50%, right? If you're given the probability, if company 2 is selected, there would be laser inkjet. It's easy to say that, right? Now if you have 3 companies and all of them have the probability or have equal probability of having an inkjet or a laser printer, if I give you any of those values, if I say that the first printer, second, or third is selected, the probability is either a laser jet or an inkjet would be 50%. You all follow me on that? But if I said the first printer was selected, the first group was selected, what's the probability that it's an inkjet or a laser, right? You'd have to go through the sequence of all possible values. It would be, if you think about selected, it would be 1, unselected, laser would be 1, inkjet 0. You could think about it all down that tree would be everything from 0, 0, 0 to 1, 1, 1, or there would be 8 possible values. Do y'all follow me on that? Exactly half of them would be inkjet, half of them would be laser. So it really doesn't matter about, there is no conditional probability in that one, but there are things that are conditional probability. And for instance, if I say that 5 people out of a class of 70 made an A, right? And so many made a B and so many made a C. Then if I say I want the probability that somebody made an A, if I say that the grade made was greater than 50 or greater than 60, then it would be conditional, because there could be a lot more or less than that. And I'll try to show you this with an area representation. So when we talk about the probability of A given B, if you have A and you have B and they're disjoint, the probability of A given B is just going to be the probability of A, because B plays no role in that. Does that make sense to everybody? If B occurs or doesn't, it has no bearing on this. But if I do this, and I say I want the probability of A given B, looking at this, it says B occurs, right? Right there. Now, what's the probability of A occurring? And what I try to do is tell you it's a ratio of areas. So if this occurs, what's the ratio of the area here to all of B? You all follow me on that? If they give you B occurs, it's somewhere in here. Now, what's the ratio of that sliver? What would be what? That's actually, take a look at that. Isn't that really the probability of A intersect B? If you take a look, does that make sense? Another way of writing this, and I'm taking this from the book. Oh, it's A intersect B given B occurs, so probability of B, because B occurs. And you have to divide out by the area of B. Think of this as an area, so the probability, if you think of the area in this sliver, right there, that's it right here. And the area in B, that would be, given B, what's the likelihood of A of occurring? And I'm trying to do this in a way that I think about these things. I always look at the ratio of areas. If you think about this is the area of B, and B happened, what's the area that this happens? The ratio of the area there divided by B. Pardon me for not being a little more exact about it. Make sense to everybody? So this is conditional probability in a nutshell. And here I want to do an exercise on, oh man, I got 2 minutes, right? So on page 43 of your book, I want to just finish with this one, and I'll get back to you on that, and then we're going to start into chapter 2, and things will make it a little more, it'll be a little clearer. But for this problem, all right, this is on page 43, and it's the one with the gas station. So there's 6 pumps at a gas station, right?
Example 135.
Example what?
1.35.
All right. A book. All right, so basically you have a gas station. And you're going to have 6 different pumps. All right, now, go ahead.
And let EI or E sub I denote the simple event that the random selected customer uses pump I.
All right, so probability of Eli, right?
Suppose that PE1 equals PE6 equals 0.10.
Let me do it over here. So the probability, let's just use smallest, of the first pump is equal to the probability of the 6th pump, right?
Correct, which equals 0.10.
0.1, go ahead.
Yeah. The probability of the second pump equals the probability of the 5th pump, which equals 15%. And the probability of the 3rd and 4th pump are equal and equal 0.25.
He gave you all that? P4
Yes, sir, equals.
0.25, okay. Give you everything.
Define events A, B, C by A equals 2, 4, 6.
So the guy selects 2, 4, 6, go ahead.
B equals 1, 2, 3. And C equals 2, 3, 4, 5.
Okay, go ahead. Oh,
It is easy to determine the probability of A equals,
say again?
it's an A and B are dependent. I think he just answers it.
What does it ask?
He doesn't really ask anything.
Wait,
It just says define, just define the events by
Determine,
that.
what?
like to determine the PA to be 0.5.
Determine what?
He just answered like.
Yeah, he just answered.
Oh, yeah, okay. But he wants P of AB in the second one. Let me just say, if you look at probability of A occurring, all right, of event A occurring, well, for that, the probability of this, or this, so you add them up, right? So the first one from pump 2, by the way, these are mutually exclusive. If they select pump 2, they can't have pump 4 at the same time. Follow me on that? So for this one, for 2, 4, and 6, well, here's 2, so it's 0.15. 4 is 0.25, so that's going to be what, 0.5 right there? And then 6 is, so it's 0.6, right? Is that the, y'all follow me on that, class? It's just adding them all up, if that's right. It should be there, though, in the example, right?
Oh, yeah. It is 0.5.
Well, wait, for this?
Probability of A is 0.5.
Well, wait. Is this right here? So that's 0.15 is 2, right?
Yeah.
4 is 0.25,
Yeah.
so that's 0.5. What about 6?
1.4.
Wait.
That's 0.4.
What is 0.4?
Yeah, 0.15 plus 0.25 is 0.4.
Sorry,
And then
0.4,
plus- and then
0.1,
plus
0.5, that's right, my bad. Keep going, trying to get this done, I'm sorry for holding it.
P, A.
Given B.
parallel with B.
So then he's asking for the probability of A given B. All right, now, remember what we just said with that Venn diagram stuff? So this is equal to what? The probability of A, what? Intersect B over the probability of B. Y'all follow me? I'm just trying to finish this in a hurry, but y'all follow me? I could draw the Venn diagram of that, but that's just what I had down, right? All right. What's the probability of A intersect B? What are you really looking at? A intersect B, the common things. Y'all follow me? They have what? 2 in common? Do they have anything else in common? No. So on top, it's going to be, they're saying B occurs. So one of these occurs. So on top here, you're going to have the probability of 2, which is 0.15, right? And it's divided by the probability of B. What's going to be the probability of B, by the way, by looking at that? Probability of B is going to be equal to the probability of 1 plus the probability of 2 plus the probability of 3, and that's going to be 0.5, isn't it? So it's this divided by 0.5, or it's equal to 0.3. I hope that's the answer.
That is the answer.
Okay, y'all follow the reasoning behind it? All right, I'll go through that. I'm going to give you some rating. I'll finish that problem I started 31 and do more with permutations and combinations on Monday and be very clear about it. And then we're going to get into chapter 2, and that's actually more applicable for everything we do as engineers. We're going to get into what we call random numbers and the probability density function and the cumulative probability, but this will make, I think that will make a little more sense. I'm sorry for botching that last part of that problem. I was thinking there's a way to do this mathematically and I couldn't. I thought I knew enough about it, but I didn't. Thank you again. Sure. And by the way, the video link, did everybody get that?
Yes, yes.
It should be accessible. N factorial over n minus k factorial. That's the way it's always going to be. Here, if you think about, we have, when we did the 3 objects, right, without replacing, it would be 3 factorial over, and it's 3 of them, so it's 3 minus 3 is 0, 0 factorial. That's exactly what, 6. That's how many different combinations we had, right? Yeah.
Sorry, I didn't mean to intrude, but could you maybe, instead of doing the entire 4-number thing, just do the front row column? And you only have 7 possible things, so it'd be,
Times, but for this, I mean, this shows you 6, right?
Yeah.
And that's right. If you think about if we had 4, so we're gonna have how many different ways can you order 4 unique things? So that would be 4 factorial over 4 minus 4 factorial, or what is that? That's 6 times 4 is 24, right? That's right. Now, all these things are different ways to do it combinationally, but there's a trick to get any sequence of numbers, the probability of getting a sequence, and I'm trying to remember it, and I'm gonna have to go and review this one. But I'll tell you the truth about this. When you see, once you do some problems and see it applied, it becomes clear. The sequencing thing, I haven't done that in a long time, but you start with, say, if you select the number n, as your first one, say it's 4 digits. The next one, if it's a sequence, is n minus 1 or n plus 1. We'll do this. Next is going to be n minus 2. And finally, it's 1, 2, 3, n minus 3. That's the first sequence possibility. Now, these are digits. They're not multiplied together. If you think about this and you raster this from 0 to 6, yeah, for 6, now you're going to find out all the possible combinations in the positive direction that can happen. You multiply that 2, that's negative. So when you do this from 1 to, actually it's 7 because you started 0, 7. He was right, 14. That's 14 possibilities for 4 digits. And we could keep on messing with that, but I'm gonna do that on Monday and try to go through it. It's one of these things.
Sort of psychotic, like I was reading the book yesterday, so it just was like,
Does this make sense what I talked about with that
Yeah.
Venn diagram business?
the textbook can sort of, like, it made my mind just like,
Uh,
I didn't know what, like, it,
The Venn diagrams, I tell you, they are so helpful and visually, because I just say it's a ratio of areas, that is the probability really. They're trying to show you that when they have an event A, the bigger A is in terms of S, the more likely it is. And you can see it much easier with a Venn diagram. It's not that abstract. The real problem with some of this stuff is the way to define the subsets, like sequential numbers. How do you do that quickly? And I'll do that on Monday. He was right about that with his counting, but it should be starting with n. Next one's n minus 1, n minus 2, n minus 3, then sequence in from 0 to 6, which are 7 values that way, 7 values the other way, so it'd be 14 total with 4 digits. Subtract that off, you gotta subtract off the 10, so it's minus 24 from 10,000, and then whatever else you said.
you can't start with 19.
Yeah, so that's.
What?
Combination.
It could, like, your pen can't be like a birthday, so it can't, the first 2 digits can't be 19.
Okay, so that's the entire sequence, 1900 to 1999, right? That's what, 100 numbers. So you have to subtract 100 from that. But we'll do that on Monday.